Hello everyone, welcome to my channel. In this video, I'll explain you how to design a laced column. So this is design of steel structure subject in civil engineering branch. So here we have to design this. This is the lacing portion. So this is the lacing portion and these are the channels placed toe to toe, not back to back, toe to toe. So we have to design for this lacing system. The question is 10 meters long column is given and the axial load is 1500 kilonewtons. The column is restrained in position but not in direction at both ends. So provide single lacing system with bolted connection. So design of the columns with two channels placed toe to toe. Toe to toe means like this. So these two are the channel sections connected with bolted connection and placed toe to toe. So for this we have to design the lacing system. So first we have to design the column. Like load is 1500 kilonewtons. I converted this into newtons and length is 10 meter. So here this is a practical subject, so we have to mostly solve the problem by our assumptions. So assuming FCD, that is design compressor design strength 135 newton per mm square. So first we have to choose the section, which section is suitable. For that we have to assume the FCD value. So area required, we know that stress equal to load by area formula. So here I converted this area here and stress here. So 1500 into 1000 divided by 135. So I got 11,111 mm square area required. But as per this condition, I mean as per this value, here I am providing area provided based on area required. So try two ISMC 350 channels. So why I am choosing this ISMC 350? Because here if you observe this area value for ISMC 350 channel section, 5366 mm square. So here we are providing two ISMC 350 channels. So if you add this 5366 plus 5366, which the value is nearer to this area required. So that's why I'm choosing ISMC 350 channel sections. So this area value RZZ, I mean ISMC 350 channel section values are available in page number 6, Steel Tables SP6 1964 book. So if you purchase this book, or if you can download through online also. So by for this ISMC 350, all these values are available. RZZ, RYY, CYY, IXX equal to IYY values. All these values are available in this Steel Tables book. You can download from internet also. And next, we have to um, area provided, that is 2 into 5366, 10,732, which is nearer to this value. And next one is the distance between two main members should be kept as to get RYY greater than RZZ, where RYY is the radius of gyration about weaker axis and RZZ is the radius of gyration of stronger axis. So here it is showing that RYY, which is radius of gyration, which is the weaker axis. So as per code table number 11, page number 45, IS 800 2007, the code is specifying actual slenderness ratio KL by RZZ, which is 1 into 10,000 divided by 136.6. L is nothing but 10 meters. So I converted it mm. So 73.206. RZZ value here, which is available in Steel Tables, 136.6 mm. So I'll show you page number 45, table number 11, IS 800 2007. Table number 11, page number 45. See, this is table number 11, effective length of compression members. So here why we are choosing this section, because in question he mentioned that the column is restrained in position but not in direction at both ends. So here the column is restrained, see, but not in direction both ends. So that's why I'm choosing this class. 1 into k value is 1. That's why I consider k value is 1. Here the formula is 1.0 into L. Okay. So after that, next we have to calculate in page number 48, clause number 7.6.1.5 KL by R. So we got the KL by R value, which is 73.206, but code is specifying that as per code we have to follow the specifications. Page number 48, clause number 7.6.1.5. see here, page number 48, IS 800 2007 code book. The effective slenderness ratio KL by R of a laced column shall be taken as 1.05 times of the KL by R. So that's why I multiplied with 1.05 into 73.206, that is 76.87. So after getting this value, we have to find load carrying capacity, because we choose ISMC 350 channel section, whether this is suitable section or not, whether the load is carrying or not, we have to calculate. So here table number 9C, page number 42, the code is specifying the values. See, design of compressive stress FCD megapascals per column, buckling class C. Why I am choosing this buckling class C? Because the channel section which we choose is belongs to buckling class C. This is also specified in the code book. Now to find out the FCD value, I did interpolation for this 76.87. See FCD, so 76.87 is nothing but the value is in between 70 to 80. So our yield stress Fy value is 250. So for this I did interpolation for in between 70 to 80 and 250. I did interpolation. So interpolation is nothing but, here see, this is 152 minus 76.87 is our value, minus 70 is here, 70 divided by difference between these two, 80 minus 70, into 152 minus 136, 152 minus 136. By doing interpolation, I got 141.0 Newton per mm square. So next we have to find load carrying capacity of this column. So that is nothing but 10,732 into 141.0. So here 10,732 is nothing but area which we provided into, this is FCD value, design compression stress. So I got 1513.212 kilonewtons, which is greater than 1500 kilonewtons. That is nothing but the load acting on the column is 1500, but the load carrying capacity is more than that 1500. So hence our column is safe. The section which we choose is safe. So now we have to consider the case of the laced columns with two channels provided toe to toe. So already I showed the diagram. So this is columns which is toe to toe, from toe to toe. So here first we have to calculate the spacing from here to here, how much spacing we have to provide it. So Ixx value, we know that already I have shown. Ixx is as per steel tables book for ISMC 350, page number 6, steel tables. Ixx value we know that 2 into 10,008 into 10 power 4 Iyy, but here the weaker axis is Iyy, So we have to calculate the momentum of inertia of Iyy, that is 2 into the formula is Iyy plus A into Yc square. Okay, A into Yc square. So this is the basic formula. We know that momentum of inertia of the rectangular formula, we know that. And next I am equating these two equations, Ixx equal to Iyy. By solving this Ixx equal to Iyy, I got spacing, that is distance from two channels, that is d equal to 267.2 mm. So I took 270 mm spacing, which is this one, spacing between two channels, 270 mm. Next, here we have to design the lacing. So let the lacing flats be provided at 45 degrees to horizontal. So this is also mentioned in the code book. So everything, every specifications will mentioned in the code book. You have to thorough with the IS 800 2007 code book. According to that code specifications only, you have to design the lacings. Okay, so here horizontal spacing of the lacing. So here horizontal spacing of the lacing is nothing but horizontal spacing is this one. So horizontal spacing of the lacing is nothing but, we know that from this distance from here to here is 270, and 270 minus 50 minus 50 minus 50 is nothing but gauge distance. Gauge distance is nothing but from this column to lacing flat distance. So both side 50 50. So I detected that. So I got 170. And next, vertical spacing. Vertical spacing is nothing but this one is the vertical spacing, which is 340. So we know the formula. I took, I mean, center of this I consider as a rectangle, sorry, right angle. So we know the formula. Half of this from here to here is 170, because this is 340. Half of the 340 is 170. So I took from here, this is right angle. So 170 into tan 45 into 2. 2 means two sides. So that's why I got 340. Two sides means I took only this right angle, and this right angle is also there. So 1 plus 1, 2. That is 340 mm. This is the vertical spacing. Again, we have to consider slenderness ratio KL by R of the channel between lacing. That is 340 by, vertical spacing by 28.3. R value, we know that for this R value, I have shown you RYY, that is 28.3 radius of gyration. So I got 12.01, which is less than 50. So this one, this is also code specifying in page number 50, clause number 7.6.5.1. 7.6.5.1. See here, code is specifying that consecutive lacing connections is not greater than 50. So which is less than 50, hence this is correct. So all these specifications are available in the code book, page number 50, which is specially mentioned for the lacing problems. Lacing design is start from 7.6, IS 800 2007, clause number 7.6, laced columns, which is page number 48. You have to follow these specifications while doing the problem. Next, transfer shear to be resisted by lacing. So this is also specified in the code book, page number 50, 7.6.6.1. See, design of lacings. So here the design started. The lacing shall be proportional to resisted total transfer shear Vt at the point in the member equal to at least 2.5% of the axial force. So that's why transfer shear Vt equal to 2.5 into 1500. The force is 1500, which is given in question. So I converted into newtons. Vt equal to 37,500. By 100 is nothing but 2.5% he mentioned, so divided by 100 I took. And next, transfer shear to be resisted by each lacing system. Each lacing system means two sides lacing systems are there, so 37,500 divided by 2, which we got 18,750 newtons. So length of the lacing equal to 270 minus 50 minus 50, that is spacing between the channels minus 50 gauge distance minus 50 gauge distance into 1 by cos 45, that is 240.45. And next, by solving this equation, I got length of the lacing, that is 240.45. Length of the lacing is nothing but length of the lacing flat. And minimum thickness of the lacing we have to provide 1 by 40 into 240.45, that is length of the lacing into 1 by 40. This 1 by 40 is also mentioned by code book page number 50, 7.6.3. I'll show you. See, so this is the thickness of the lacing member. Thickness of the lacing flat shall not be less than 1 by 40th of its effective length for single lacings. So here we are designing single lacings. As per code, 1 by 40th of length of the lacing, effective length. That is, I got 6.01125 mm. So here I got around 6.0. So I am considering 8 mm flats. I am using 8 mm flats for this. So minimum width of the lacing, if 16 mm bolts are used, so 3 into 16, that equal to 48 mm. So clause number 7.6.2, page number 50. Width of the lacing bars here. In bolted and riveted construction, the minimum width of the lacing bar shall be 3 times the nominal dia of the end bolt. So that's why I am considering as 3 into 16. As per code, we have to follow these specifications. So I got 48 mm, I am considering 50 mm. That is nothing but minimum width of the lacing. So I'll show you in the diagram. So this is the width of the lacing flat, and this is the length of the lacing. 50 ISF, Indian Standard Flat, 8 mm. Okay, so like that we got 50 here and 8 mm is here. So 50 by 8 mm. And next, hence we provide 50 ISF 8 mm. So next, sectional area, that is area of this flat, 50 into 8, L into B, 400 mm square. So R minimum equal to, we know that rectangular formula, BD cube by 12 by area. So 2.308 mm. BD cube by 12. B 50 into D means 8 divided by 12 by area. We will get R minimum. Next, KL by R. So KL by R is nothing but, we know that K equal to 1, 270.45. Already we got the value 270.45 by multiplying that and divided by 2.308. So I got 117.179, which is less than 145. The code is specifying again 7.6.3, page number 50. In page number 50, 7.6.6.3, the slenderness ratio KL by R of the lacing bars shall not exceed 145. So that's why less than 145. So this is all these steps are, I mean, taken from code book only. You have to follow the design procedure. First go through with the code book, page number 50, design of lacings and everything before going to solve the problem. Hence the provided flat is safe. Flat is nothing but a lacing bar which is safe. Now we have to design the connection. Strength of the 16 mm bolt, nothing but, just now we designed all these flat, this lacing flat, horizontal distance, vertical distance, everything. Now we are considering this bolting connections. So strength of the 16 mm bolt. So while we are doing this bolting sections and everything, we have to follow the code rules. Page number 75, again for connections, code is specifying that, page number 75. Page number 75, clause number 10.3.3, which is 10.3.3, shear capacity of the bolt. VDSB equal to VNSB by gamma m naught. So VDSB equal to VNSB by gamma m naught. So first we have to find the VNSB value. VNSB equal to FU by root 3 into NN ANB plus NS ASB. So here FU by root 3 NN ANB plus NS ASB. So NS is nothing but shear planks at shank. Shank means when there is a bolt, the threaded portion is also there. So bolt and nut. For that, for example, this is the bolt. This is plain portion and this is threaded portion. So NS equal to shear planes at shank and NN equal to number of shear planes with threads. So this is the threaded portion NN. NS is shear planes at shank, which is 0. There is no shear here because there is no connection for the bolt and nut. So that is 0 and NN equal to 2. Why? Because two sides we will do the connections. So here A and B, that is nothing but 0.78 into pi by 4 d square. A and B is nothing but net shear area of the bolt at threads. Here this is the, while we connecting the bolt, here it will the connection. So net shear of the bolt may be taken as area corresponding to root diameter at the thread. 0.78 into pi by 4 d square. That is nothing but circle area. 0.78 into pi by 4 d square is 16, 156.83 into mm square. So I substituted all these values in the equation. We know F equal to ultimate stress, which is 400. This value is also available in code book. 400 by root 3 into and then 2 into 156.83. I got 72,429 newtons. So I substituted VNSB value in this equation. So we know that gamma m naught is 1.25, which is available in table 5, table number 5 in IS 800 2007. VDSB equal to 72,429 divided by 1.25. This is the formula and these are the values. 57,946 newtons. And again, we have to calculate strengthened bearing. Just now we calculate shear capacity, next bearing capacity. So bearing capacity formula is also available in the code book. So this is the clause number 10.3.4, bearing capacity of the bolt. The design bearing capacity of the bolt on any plate VDSB equal to VNSB by gamma MB. That is the formula. The same formula I have mentioned here. So here again in this VNPB we have to find, in the VDPB we have to find the VNPB. So VNPB equal to 2.5 into KB into D into T into FU. So KB is nothing but smaller of all these values. The same thing I have solved here. See, VNPB equal to 2.5 KB into T into FU. So first we know the T value, we know the FU value, we know that, we don't know about the KB value. We have to find the KB. So code is mentioned that KB is smaller of all these values. So E is nothing but edge distance, which is 50 divided by 3 into 18. D naught means diameter of the hole. So hole diameter is nothing but, diameter of the bolt is 16 mm, but code is specifying that we have to consider extra 2 mm for the hole diameter. So 3 into 16 plus 2, 18. I got 0.9259. P by 3D naught. 50 by same 3 into 18 minus 0.25. This is available in code book, the formula KB value. Okay, and next FU by FU 1.025. That is nothing but 410 by 400 and 1. All these given by code book. I will show you here. All these values. E by 3D naught, P by 3D naught minus 0.25, FUB by FU and 1. So by solving all these values, whichever is the smaller, we have to consider that value. So the smaller value is I'm considering the smaller value, which is 0.67, this one. So I'm substituted all the values in the VDPB, 2.5 into 0.67 into 16 into 10 into 400. This is the formula. 2.5 into kb value, 0.67 into thickness into fu. So I substituted all the values. 1 by 2.5 is nothing but a gamma m naught partial safety factor, which is available in table 5, code number IS 800 2007. I got 85,760 newtons. So the bolt value is, according to code book, the bolt value is whichever is minimum, we have to consider that, because there might be a chance of failure if the minimum value is there. So 57,946 is the minimum when compared to bearing and when compared to shear. So that's why bolt value is 57,946 newtons. So number of bolt required we have to calculate. So the load is 18,750 each flat is carrying. Already we calculated that. I'll show you. So here, transfer shear to be resisted, that is 37,500 divided by 2, 18,750 newtons. So 18,750 divided by 57,946, I got 0.323. So provide one bolt. So one bolt is nothing but, this is one bolt for lacing flat connection, and this is one bolt. Check for strength for lacing. Same KL by R, I got 117.179. We have to check this KL by R, lacing system. Again the same interpolation before we did, like that. Page number 42, table 9C, page number 42, table 9C. Again the interpolation for this value 117.179. So KL by R value 117.179, which is 110 between 120. So 110 and 120. So Fi is yield stress, which is 250. So 110 and 120. So these are the values: 94.6, 83.7. So 94.6 minus 117.179 minus 110. So I think you know about the interpolation. And 120 minus 110, which is in between value. So I got the interpolation 86.77 Newton per mm square. So here load carrying capacity in compression, that is 86.77 into area of the flat, 50 into 8, that is 34,708, which is greater than 18,750 newtons. So hence it is safe. This is the value which the load carrying capacity of the flat, load of the flat, and this is the load carrying capacity of the flat. So the value which is greater than the load, so hence our flat is safe. Next, tie plate. So tie plate is nothing but which is connected for to withstand this column. So this is the tie plate. We have to consider a tie plate. So the tie plate is effective depth of the tie plate is S minus 2y, 2 into cyy. That is spacing we have to consider. So 270, S is nothing but spacing, 270 minus 2 into cyy value, which is available in steel table book. Starting, I mentioned the cyy value for the ISMC channel section. So cyy is 24.4 mm. So these values are all available in steel tables book. So I got 221.2 mm. So 2, which is greater than 2 into 90, 180 mm. This is also available in the code book. For the tie plate design also, code is specifying the specifications. We have to follow those specifications only. In page number 51, clause number, I'll show you. In page number 51, clause number 7.7.2.3 here, which is not less than the tie plate thickness of the plates. Here the size of the plates, all these mentioned in the code book. You have to follow the code book provisions. Okay, next, Required overall depth of the tie plate, which is 220. I got 221.2. I'm considering this as 220 plus 2 into 16, that equal to 250 mm, nothing but diameter of the bolt. So I got 250 mm. I'm considering 300 mm plate. Provide a 300 mm plate to withstand the design, sorry, tie plate. So thickness of the plate, again, this is available in page number 51, clause number 7.7.2.3. The code is specifying the same thing, like 1 by 50th times of 250 minus 2 into 50, that is 3 mm I got. So minimum we are providing 6 mm thickness of the tie plate. So here in the code book mention the clause. Tie plates are members provided the ends of batten and laced columns shall be designed by the same method as battens. In case case of the tie plate and fastenings to be incapable of carrying the forces of which the lacings or batten has been designed. So like that, code is specifying all these conditions as per battens he mentioned. So 7.7.2.3. So this is the 7.7.2.3 size. So we have to, as per code only, we have to design. So here I am considering 1 by 50. 1 by 50. Why I am considering 1 by 50? Here code is specifying the thickness of the batten or tie plates shall be not less than 1 by 50 of the distance between the innermost connection lines. So that's why I am considering 1 by 50. I got 3 mm, so I provided 6 mm. Provide tie plate of size 250 by 300 by 6 mm. So I'll show you in the diagram tie plate. So this is the tie plate. This is the tie plate, 300 mm depth, 250 mm, 300 mm, and 6 mm thickness. Okay, like that you have to design this lacing system. I hope you understood my problem. If you have any doubts, please mention in the comment section. This is completely a practical problem. You have to go through with IS 800 2007 code book to know more about the design part. Thank you so much. Thanks for watching my videos.